Welcome back to Bite-Sized Breakthroughs, where we break down the latest advancements in AI research, making complex concepts digestible for everyone. Today, we're diving into a groundbreaking paper titled Learning Transferable Visual Models from Natural Language Supervision, which unveils a new approach called CLIP. That's right, Alex. This paper, published by researchers at OpenAI, has the potential to revolutionize computer vision. So let's get right into it. Dr. Turner, can you give us an overview of the challenges that traditional computer vision systems face?
Sure, Alex. The major hurdle in traditional computer vision is that these systems are trained on fixed sets of predetermined object categories. They're trained to recognize things like cat, dog, or chair. But when you want to teach them a new concept, like a specific breed of dog or a particular type of chair, you need to provide them with a ton of additional labeled data. This makes them inflexible and limits their usefulness for real-world applications.
So they're essentially limited to the categories they've been explicitly trained on. That sounds like a big problem. What's the solution that this paper proposes?
The breakthrough lies in the realization that natural language, the language we use every day, holds a wealth of information about the world. The paper argues that we can learn directly from raw text about images. They essentially teach a system to understand the relationship between images and their corresponding text descriptions, bypassing the need for traditional labeled data.
That's fascinating. Professor Spectrum, this concept of learning from natural language supervision is pretty revolutionary. Can you tell us about the historical context and how this approach builds upon previous work?
Absolutely, Alex. The idea of using natural language to learn about images isn't entirely new. Researchers have been exploring this concept for over 20 years, focusing on tasks like image retrieval. Early efforts were limited by the complexity of natural language processing and the lack of scalable pre-training methods. However, recent advancements in natural language processing, particularly the development of powerful language models like GPT, have paved the way for more effective and efficient approaches.
So this paper takes advantage of these advancements in NLP to create a new method called CLIP, which stands for Contrastive Language Image Pre-training. Dr. Turner, can you explain what CLIP does and how it works?
CLIP's core innovation is its use of a contrastive objective. Instead of directly predicting the exact words of a caption, it learns to predict which image goes with which text description. This makes it more efficient and scalable. Think of it as a multi-choice quiz. CLIP is given a bunch of images and their corresponding text descriptions. It needs to figure out which image matches each text, choosing from a set of possible pairings.
That makes sense. So it's learning the relationship between images and text without needing to understand the exact words used. But how does CLIP actually learn this relationship?
CLIP uses two encoders, one for images and one for text. The image encoder extracts visual features from the image, creating a kind of visual fingerprint. The text encoder processes the text description, understanding its meaning and creating a semantic representation of the text. Both encoders are trained simultaneously. The goal is to make the visual fingerprint and the semantic representation of the text as similar as possible when the image and text are correctly paired, and as different as possible when they're not.
That's fascinating. So CLIP is basically learning to understand the link between what's in an image and what a text says about it. Professor Spectrum, can you elaborate on how this method compares to existing approaches?
You bet, Alex. Previous work in this area often relied on smaller datasets and used predictive objectives, which were less efficient in scaling to large datasets. CLIP's contrastive approach is a major step forward, enabling the training of much larger models on massive datasets. It also improves the robustness of the learned representations. This means the model is less likely to be fooled by small changes or variations in the images, making it more reliable.
So this contrastive learning approach gives CLIP a significant advantage over previous methods. But how do we actually test CLIP's performance? Dr. Turner, can you walk us through the experimental setup?
Right, Alex. The researchers evaluated CLIP on two main fronts. First, they tested its ability to perform tasks without any dataset-specific training, a technique called zero-shot learning. They did this by giving Clip a set of text descriptions of new concepts and asking it to classify images based on those descriptions. It was like giving it a pop quiz on concepts it hadn't been explicitly taught. The second evaluation method was called linear probing, which tests the model's ability to learn general visual representations. They extracted the image features from Clip and trained a simple linear classifier on those features. This allowed them to compare Clip's performance to other pre-trained models.
So the zero-shot evaluation looks at Clip's ability to generalize to new tasks, while the linear probe measures its ability to learn generalizable representations. What were the key findings of these experiments, Dr. Turner?
The results were quite impressive. Clip achieved state-of-the-art zero-shot performance on numerous computer vision benchmarks, often outperforming or matching fully supervised models without requiring any dataset-specific training. For example, Clip matched the performance of the original ResNet 50 on ImageNet zero-shot without needing to use any of the 1.28 million training examples it was trained on. It also demonstrated high effective robustness, meaning it was less prone to being fooled by changes in image distribution compared to models trained solely on ImageNet. These results suggest that Clip's representations are more generalizable and less susceptible to spurious correlations.
Wow, those results are truly impressive. So Clip is not only capable of learning new concepts on the fly, but it also learns more robust representations. Professor Spectrum, what are some of the implications of this for different fields?
Alex, this research has the potential to revolutionize numerous applications in computer vision. Imagine a world where you can search for images based on natural language descriptions instead of relying on keyword searches, or a system that can automatically caption images, providing rich information for visually impaired individuals. Clip opens up a plethora of possibilities in image retrieval, object recognition, scene understanding, and beyond. It also has implications for creative applications, user interface design, and even healthcare.
That's a fascinating range of potential applications. But with this kind of power comes responsibility. Dr. Turner, what are some of the limitations of Clip and the potential challenges we need to be aware of?
Yes, Alex, it's essential to acknowledge the limitations of this research. While Clip demonstrates impressive performance in many areas, it still has weaknesses. For instance, it struggles with tasks involving fine-grained classification, like differentiating specific breeds of dogs or models of cars. It also has difficulty with abstract reasoning tasks and novel tasks that weren't part of its training data. Moreover, Clip's reliance on a web-scale dataset raises concerns about societal biases that may be present in the data. This could lead to the model amplifying existing inequalities, requiring careful scrutiny and mitigation strategies.
That's a crucial point, Dr. Turner. The paper itself acknowledges the potential for biases in Clip, and it's something we need to pay close attention to. Professor Spectrum, can you elaborate on how these biases might manifest and the challenges they pose?
Certainly, Alex. The paper provides some initial analysis of biases in Clip, but it's important to understand that this is just the tip of the iceberg. The researchers found that Clip exhibits biases related to race, gender, and age, likely stemming from the biases present in the web-scale dataset it was trained on. For example, they observed that the model was more likely to misclassify images of Black individuals as non-human animals. This highlights the crucial need for ongoing research and development of strategies to mitigate biases in general-purpose AI systems. We must be vigilant about the potential for harm and ensure that these technologies are used ethically and responsibly.
It's clear that this paper raises important questions about the ethical implications of AI. Dr. Turner, what are some of the future directions for research in this area?
The research community has a lot of work ahead. We need to develop more efficient and scalable training methods, improve Clip's performance on specific tasks, and develop new benchmarks to evaluate zero-shot transfer capabilities more effectively. Addressing the challenge of brittle generalization and mitigating societal biases are critical priorities. We also need to explore ways to combine Clip's strengths with more efficient few-shot learning strategies to better align with how humans learn.
Dr. Turner, Professor Spectrum, thank you both for shedding light on this exciting and complex research. It's clear that CLIP is a significant advancement in computer vision, but it's also a reminder that we must approach these powerful technologies with caution and responsibility. We need to continue researching and developing these systems with a focus on ethical implications, mitigating biases, and ensuring that they benefit humanity. Absolutely, Alex. The future of AI is bright, but we must be mindful of the challenges ahead. Thank you for joining us on Bite-Sized Breakthroughs. Stay tuned for more exciting updates from the world of AI.